Okay, so let's get started. Uh, Today we'll look at output stages, and in last lecture, so this is how the outline of this one and the next lecture would be. We'll look at class A, common emitter and common collector amplifiers, class B push-pull amplifier, and class AB amplifier. All right. Anyway, in the last lecture I was telling you that most amplifiers are multi-stage, and the reason why they are multi-stage amplifiers are that a single stage by itself cannot satisfy all the requirements. And the reason why a single stage cannot satisfy all the requirements is that trade-offs exist among amplifiers characteristics here. If you try to build up gain, then we have seen that you lose maybe the input resistance or you lose the output resistance here. And as a result of that, what happens is you have to create stages which specialize in one thing. For example, the input stage may specialize in input resistance, providing you with large input resistance and maybe low noise performance here. The middle stage here, you may have a stage which specializes in gain, building up sufficient amount of voltage gain. And then you may have a stage at the output which specializes in delivering power to the load here. So when you have a load connected here, you want low output resistance, you want power to be delivered to the load, and you want it to be efficient here. So the requirements are different for different stages, and so we have stages which specialize in one particular aspect here. So today we are going to look at the stage which specializes in delivering power to the load here. And so what we are talking about then is a very basic principle, which is principle of division of labor. So as I said, most amplifiers are multi-stage. So here is an amplifier which may specialize in input resistance. And this may specialize in gain. This may specialize in output resistance. Specialize meaning providing low output resistance and providing power here. This is the place where you need to provide power to the load here. So all these different stages specialize in different aspects. Okay. And through cooperation amongst these three different stages, then you can build an amplifier which is much better than any single stage amplifier. Okay. So that's the idea here. And this is the focus of our interest here, output stage here. Now it's obvious that output stages are very important. You're building up gain and input resistance and all of that with the ultimate purpose of what? Delivering power to the load, right? So if you mess up here, all the things that you've done good here will of no avail if this particular stage is not proper here. Okay, so output stages are obviously important, and let's look at some of the important characteristics here. So in this particular lecture, what we in this discussion we'll concentrate primarily on efficiency. All right, we've already seen that if you want to build an amplifier with low output resistance, what is it that you have to do here? Okay, so here is an amplifier, and we have a load resistance, and obviously we said that when you want to interface it to a load here, you want low output resistance here. You can see here that you want voltage swing, obviously, because this is the place where the swing is going to be the highest. So voltage swing is obviously important, and you don't want to distort your signal. Whatever was the signal here, you want an amplified version of signal to go to the load here. So obviously voltage swing without distortion is important. So we have seen these two things earlier. The other thing is, this is the place where you're delivering power. So you have some load power PL. And as we have seen earlier, the power that you take from the input is very small. Most of the power comes from the supply here. So this is the power, PS refers to power that comes from the supply here. And so we have a notion of efficiency then. This is the power that you take from the supply, and this is the power that is delivered to the load. Obviously, you want all the power that you take from the supply to go to the load here, because any power that doesn't go to the load is lost as heat in the amplifier itself. So efficiency, then it makes sense that you can define efficiency as PL, load power, the power that you are interested in, divided by the input power here. Now remember, when we say input power, it's not the power from here. Okay, it's the supply power taken from the supply voltages here. So efficiency then is PL by PS into 100 here. So when I'm building my output stage, then I'm interested in building a stage here which will give me large efficiency. Ideally, of course, I would like efficiency to be 100%. Okay. So if PS is the power taken here, PL is the power given to the load, and efficiency is PL by PS, then 1 minus eta by 100 into PS is the power that is dissipated in the amplifier itself. And that power, as I said, is dissipated as heat. If you have resistors, some of the power is dissipated in the resistor. The remaining would be dissipated in the transistor itself. Okay. And so besides the fact that, you want efficiency obviously to be high, one of the consequences of a smaller efficiency is, note that a lot of power gets dissipated here. And as a result of which, the transistors heat up, and then you have to take special precaution in order to prevent the transistor not getting damaged because of the heat here. Okay. So transistor selection becomes crucial here at the output stage here. As an example, let's say 3 watts of power is being delivered to an 8 ohm, say it's a loudspeaker, and you're taking 10 watts from the power supply here. So obviously 7 watts is dissipated here. And efficiency then is 3 by 10, 30%. Now, one has to ensure now that the transistor that you use for building the amplifier, they can withstand the 7 watts of power dissipation. Okay. And not only that, note that if I have 3 watts of power at 8 ohms here, the voltage that I'm building up, you can calculate if it's a sinusoidal signal, the voltage is around 7 volt here. So you want your transistor to handle 7 volt properly at that level of power dissipation. And also, if the current here, if I calculate 7 volt is the peak voltage here, 7 divided by 8 ohms, so I have 0.87 amperes here. So you want your transistor to be able to handle, because who's supplying this current is the transistors inside. So you want your transistor to handle this much current, this much voltage, and if you have only one single transistor and all the power is dissipated in it, then this much power as well. Okay. So transistor selection then becomes crucial here. You have to pay attention to the current limit of the transistor. You have to pay attention to the voltage limit of the transistor and also the power limit here. Okay. So as an example, if you look at this 2N222 here, all the manufacturers will list for you the maximum rating of the transistor here. For example, the manufacturer says here that the collector base voltage or collector emitter voltage is a maximum of 40. So 40, of course, is very large, will not bother you. Emitter base voltage is given here. Collector current, look at the collector current. It says collector current maximum is, continuous value of collector current maximum is 600 milliamperes here. And 600 milliamperes here, this is saying peak current is 870, may not be suitable. You have to investigate in more detail because it's talking about continuous here. Further, look at that. The manufacturer is telling you what is the total power dissipation that your transistor can handle. It says around 625 milliwatt of power your transistor can handle if the ambient temperature is 25 degrees Celsius. If the ambient temperature rises to 40 or 50, the power rating of the transistor goes down. So you have to look at all of these values that are listed here, and on that basis decide whether a particular transistor is appropriate for your amplifier or not. See, at the previous stages, for example, at the gain stage, the currents are low. The voltages may not be as high. Power is obviously not that high. You don't have to worry too much in the previous stage. But at the output stage, the current is the highest current because, that's where you have to deliver power. The dissipation is highest. So you have to start worrying about these things here. Okay. Now, when we discuss load power, obviously my signal can be a speech signal or a video signal or whatever. But for the sake of discussion, when we talk about signals, we take it as a sinusoidal signal here. So when I talk about power and efficiency, I'll assume that this is a sinusoidal signal here. And so VIP will refer to peak value or the magnitude. And naturally, if my input is a sinusoid, I would like my output also to be a sinusoid here. And power that is dissipated in the load, then RL, is then given by. So when we talk about power, we're talking about average power. We're not talking about instantaneous value here, okay? So we're talking about average power. So average power, all of you know, is V square by RL, and you integrate and average it, and you get the average power for a sinusoid is peak value square by 2RL. So that's the average power, which is dissipated in the load. So that's easy. We have a load current here. If I have a voltage which is sinusoidal, so I have a load current also. And all of these are trivial. Power we can also write in terms of IL square RL by 2 instead of V square by 2 RL here, or you can write it as product of the two here. Okay. The input power. The input power is, again, let me emphasize, we're talking about this power, supply power. So what will happen is you are going to draw some current from the supply voltage here. So the power that you take from the supply, again average power, PS will be equal to 1 over T, 0 to T. T is a one cycle of the sinusoid. VCC, this is my supply voltage, multiplied by IS. IS is the current that I'm drawing from the supply, DT here. So you have to do this average. And because VCC is a constant, I can write power drawn from the supply as VCC into average value of this current here. Because 1 by T, 0 to T, IS will be simply average value of the current here. Okay. So whatever is the average current that you draw from the supply multiplied by VCC, and you get the power that you are sucking from the power supply, VCC. Okay. All right. Sometimes we have dual power supply here. And in that case, you have a power which is coming from the positive supply here, current ISP here, and your power which is going into your negative supply here, ISN here. And then it's easy to show that the power dissipation will be VCC multiplied by average power drawn from the positive supply here, and VEE multiplied by average power that you that goes into your negative power supply here. So that's the total power here. And in most cases, VCC is equal to VEE here. So both are the same. And very often the circuits are symmetrical. Positive cycle part of the circuit is same as negative part. And therefore what would happen is ISP will be equal to ISN also. So the total power then will be twice VCC into ISP, whatever is the power taken from one supply many times. Okay. All right. So all that is related to supply voltage here. So coming back to a single supply here, power supply then taken from the supply is VCC into IS average. Power delivered to the load is V0P square by 2RL. We can take the ratio and calculate what the efficiency is. So efficiency in terms of percentage will be, so rearranging all these terms here, we can write it as VOP by VCC here, VOP by RL by IS average here. Okay. So this tells you now that if you would like to maximize your efficiency here, okay, note first important thing, the VCC is fixed for you. VCC is fixed for you, and in many of the amplifiers you'll find that what happens is you take this amplifier, so there is a biasing current which is going in, which is a DC, and on top of the biasing current, what you have is, depending on how much current is to be delivered to the load, the IS will have a sinusoidal current here. But when you average out of the, take the average of the IS, what would happen is the average of the sinusoid goes to 0. And so this IS average then practically becomes as the bias current, whatever is the bias current that goes into your amplifier here. Okay. So note what happens then is that this denominator then is a fixed value. VCC is fixed for you. And once you bias the transistors and all that, IS may also get fixed here, IS average. So denominator is fixed. Numerator then, V0P, RL also, once your load is fixed, RL is also fixed here. So efficiency then depends on how much voltage you build up here. Now note that if you apply a small signal here, if the input signal is small, then obviously V0 is also going to be small and efficiency is going to be small. Now efficiency will increase as you increase the value of V0. Okay. And of course, you know that there's a limit to how large a V0 you can build. Because after a while, if you keep on building V0, if you can keep on increasing Vin, it's not that V0 will keep on increasing. Eventually what will happen is distortion will start occurring, and you cannot handle that much distortion, or your application cannot tolerate that much distortion. So what this is pointing out is that efficiency increases with the output voltage here. The larger the power that you have to deliver to the load, PL, the larger the PL, the larger the V0P will be, and in general, then the efficiency would be largest here. Okay. So for an amplifier like this here, note that you want a sinusoid here. So what you would be doing is basically biasing this particular amplifier. This is 0 here, this is VCC here. So what you would do is you would normally bias this amplifier. I'm taking a simplistic view right now. You would bias the the amplifier here such that the DC value of the output voltage here is maybe in the middle, 0.5 VCC here. Okay, so DC value here is in the middle, so that when the sinusoid comes here, you can go as much in the positive direction as you can go in the negative direction here. And so if you bias it in the middle here, then you note that the maximum value of V0P that you can get is half VCC. So VCC is the net supply voltage here. You bias it in the middle. If you bias it closer here, you'll get even less than half VCC. If you bias it below that, again, you'll get less than half VCC here. Okay, so as a simplistic view, you may bias it right in the middle, and then you'll get 0.5 VCC here. So the maximum VOP that you can get is VCC by 2. So VCC by 2, so this is telling you eta will be equal to 25% multiplied by VOP by RL divided by IS average here. Okay. So one of the things that you should try and do is that design the amplifier in such a way that is capable of giving you this much swing. This is the maximum that you can get, as you can see from this particular figure. And therefore, you should design it such that you approach this particular value. If you don't design it properly, you may fall short of that. Because if you don't design, meaning if V0 DC is, let's say, not 0.5 VCC, say it is 0.25 VCC. If it's 0.25 VCC here, is way low here. And obviously, then you can't get the highest possible value of V0P. Okay. Same thing happens in a dual power supply here. In this case, when I have a dual power supply, positive and negative parts are the same. So what I would do is I would bias it at 0 volt here, in the middle here, 0 volt. And in that case, my VOP can go up to positive part here, VCC here. And on the negative side, it can go to minus VCC here. That doesn't mean that efficiency increases. I have two power supply here. And therefore, note that the power drawn from the supply is also twice. So although you can get VOP equal to VCC here, efficiency is still 25 multiplied by this particular term. Okay. So in this case, when you have a dual power supply, you would like to bias it at around 0 volt and try to get VOP as large as the supply voltage here. So this is what we call as rail to rail swing. You want your output voltage to go to positive rail, and you also want your output voltage to be able to go to negative rail here. All right. So that was the background. Let's now look at, is my common emitter stage a good output stage? Okay. So this is the simple common emitter stage that we'll take. You know, we could have taken a R1 and R2 and RE and all of that, but that slightly complicates the analysis. So I'll take the simple common emitter stage here. So efficiency, we know now it's a single supply. We know efficiency is given by this factor here. V0P by VCC and V0P by RL by ICC here. ICC is the net current that goes from the supply here. I should have written here IS. Okay, so now the issue is, how do I design this amplifier to give me the maximum efficiency? Now, note that efficiency depends on V0P here. So how large a VOP can I get here? What is it determined by? Well, this is IS average here. So, okay. So if I look at, so in this case, IS average, note it should have been IS average here. So IS average is the current taken from here. Part of the current goes here and another part goes here. Now the current that goes here is the base current. The current that goes here is the collector current. And obviously I can neglect this particular part here. So basically the power that comes from the supply is nothing but the current that goes here. And the current that goes here is the current that goes into the collector will have a DC component, which is ICQ, plus a sinusoidal component, which goes into the load here, as well as into the transistor here. Sinusoidal will average to 0 here, and IS average then will be approximately equal to ICQ here. So efficiency then I can write as 50 VOP by VCC, peak value divided by RL, and this is nothing but the bias current of the transistor, ICQ here. Okay. So that's a reasonable assumption that the current here is negligible as compared to the current here. This current has a DC part, which is ICQ, plus a sinusoidal part. Whatever is the sinusoidal part averages out to be 0. And so this current then, the current that you draw from the supply is practically equal to ICQ. So that's the efficiency here. So we would like to design this particular amplifier such that the efficiency is as large as possible here. So we would like to choose, let's say, VCC, RC, RB, all of these quantities we would like to choose in order to maximize my efficiency here, while delivering the power that I'm expected to deliver to the load here. Okay. So the issue then becomes in many of them is, how large a VOP can I have? And that we've already seen also how small a ICQ can I have, right? So you want to make V0P as large as possible, or this ratio as large as possible, and you want ICQ to be as small as possible here. And so we know the limits are the following. Limits on V0P are that might, I can have V0P as large as possible, but I must make sure that my transistor does not go into saturation. And that's the limit that comes from saturation. And this is the limit that comes from harmonic distortion. We have seen both of these limits earlier, that these are the two limits that decide my the value of V0 that I can have. Okay, so this will tell me the highest V0 that I can have, and once I have the highest V0, then it will tell me the highest efficiency that I can have. Okay. All right. So now what we'll do is, instead of doing more of analysis, we'll take up an example, and let's see how common emitter amplifier behaves. Okay. So let's take, suppose, a hypothetical example. You are a engineer in a, let's say, analog circuits company, and your boss asks you to design this amplifier, right? He says, give me an amplifier which will give you a power of 20 milliwatts and across a load of 100 ohms, and the supply voltage is 5 volt, right? So it's a simple design, and you have a day's time to come up with the design here, right? So what do? You've been given a task to design an amplifier, so of course you ask around. You ask your colleagues whether he has a ready-made design or not, right? Why reinvent the wheel? So, well, you're lucky. Your friend says, I had done a design maybe a year back for 5 volts. So I have a design available, and why don't you try it out, right? So now here is a design which is already available for 5 volts. Now you have to see whether the design makes sense for you, right? It was done for in a different context. So how do I check whether this design will work for me or not? Some design already exists and you want to evaluate. Is it good enough for your application? What do I do? Well, how do I start? Well, given any amplifier, what you should do is first, let me calculate his bias point, right? If you don't know where to start, well, let me just, make a beginning. And bias point calculation is easy. This is 0.7 here. So VCC minus 0.7 divided by this one will give you IB. IB multiplied by beta will give you. So bias point is 12.5 milliamperes. VCEQ is 2.5 volt. All right. So you've done the bias point. Now, how should we proceed and check whether this is okay or not? Now note, PL is given here, 20 milliwatts, and RL is also given. So I take this PL equal to V0P square by 2RL, right? And from there I figure out that I need a peak voltage of how much? 2 volt. If I want to deliver 20 milliwatts to my load here, I need to have a maximum output voltage here of at least 2 volt here, right? So what do I do next now? Check whether this amplifier is capable of giving me 2 volts output swing or not. How do I check? Well, I check, will it go into saturation? This is the constraint that tells me whether the transistor will go into saturation or not. So I have 2.5 here. This is my saturation voltage. So I check V0P. Is it less than 2.3? I'm lucky. So it's less than 2. 2 is less than 2.3. So that's fine. So you're feeling optimistic. Maybe it will work, right? What is the other constraint you should check? Distortion, right? So you should check whether it satisfies this constraint or not. Now, luckily, your boss didn't tell you anything about distortion, right? There's nothing on distortion written anywhere. So what do? Well, you have a V0P of 2 volt. You have ICQ, you have RC, RL, and all that. So you decide to calculate what is HD2. Let me just calculate what is HD2. And it comes out to be 60%. All right, 60%. So he has not told you anything about distortion, but I'm sure you'll be ashamed of giving an amplifier with 60% distortion, right? So you won't want to do 60% distortion because he'll get back to you once he uses an amplifier like this here. So what do you do now? So here is a design that your friend gave, and you evaluated it, and you're finding that it's giving you 60% here. Okay, distortion here. So what do? Well, maybe you try to find out, now that you see 60%, you try to find out, let's say, what is the best that this amplifier can do for me. Okay, obviously then for this power and these constraints, it's giving me 60%. You know that an amplifier, to be called a reasonable amplifier, should have a distortion of how much? 5, 10 maybe. Okay, so you decide, okay, let me see what this amplifier can do for me if I put 10% harmonic distortion. So you put 10% harmonic distortion here, then you calculate this, and you find, well, if for 10% harmonic distortion I can build up only 0.33 volts here, and then you calculate the power. So it's V0 P squared by 2 RL. It comes out half a milliwatt, right? And you calculate efficiency. Efficiency will be this power divided by the VCC into ICQ here. So 5 volt multiplied by this one. So you calculate efficiency of 0.89%. And so now you have an amplifier which looks reasonable at 10% harmonic distortion, but it gives you only 0.55 milliwatt here. And you are being asked to design for 20 milliwatt here. And that too, imagine now, you can't say to your boss, I'll give you half a milliwatt, and that too at 0.89% efficiency, right? So you are in trouble now. What do? Huh? Well, you should not give up so easily. You should not trash this particular design. You should see now is, so this is what the requirement is, and this is what you're getting, right? So now maybe you'll think, okay, this amplifier has not been designed for my application, right? It was a design which was already available, and when I'm evaluating it for my application, I'm finding all these terrible numbers here, right? So you decide now to, you're reluctant, but you have to now redesign it, okay? You have to redesign your amplifier, and you can't change the supply voltage because he has said that it has to run at 5 volt. Okay, so you redesign. So now when you redesign, so you have to now figure out what is RC and RB. Okay. So you want to know, well, what is the best that this amplifier can do? If I have 5 volt here, and suppose I have RC, RB, and all of that is there. Suppose I design it in the best and optimum possible manner. What is the best capability of this amplifier here? Okay. So how do I do that? Well, PL is V0 squared by 2 RL, and all that is fine. Now look at the thing here. I have so in order to get the highest power, what you should try to do is get the maximum output voltage here. And you know that there are two limits on output voltage. Output voltage is less than, there's a limit here which comes from saturation, and there's a limit here which comes from harmonic distortion. And when you examine these two limits, you see that to make V0P large, you should make ICQ-RC small. But when you examine this, you find that to make V0P large, you have to make ICQ-RC large here. And we've already seen the best V0P you will get when you balance these two. So you equate both of them together. You equate both of them together, you do some algebra, you get this expression. All right. So now that you have this expression, you want to know what is the best that your amplifier can do. So even without designing, what is the best V0P that you can have? This factor, note, RC plus RL by RL can be at the most. If you choose RC very small, at the most this factor can be, 1. You want this factor to be as small as possible here in order to make V0P large. So at the most you can have it equal to 1. So you take this equal to 1 and you say V0P has to be less than or equal to this value here. That's the best that I can do because I've taken all the constraints into account, and the best I can do for this factor is 1. And so V0P has to be less than this value here. And you calculate for 10% harmonic distortion, it comes out to be 1.43. And then you calculate power, it comes out to be 10.2 milliwatts. So what do? That's the best that this circuit can do. Well, so you go to your boss and you tell him that I can't give you what you are asking, So I'll give you maybe 10 milliwatts is the maximum that I can give you if you have a supply voltage of 5 volt and RL equal to 100 ohms, right? So this is what you have found, right? You've taken this particular circuit, you've done the optimum design, and you're finding that the best that you can do is 1.43 volts and power will be 10.2. So then the reaction of your boss is, okay, you say 10 milliwatts. So he says, okay, give me 9 milliwatts. All right, give me 9 milliwatts. All right. So you feel happy. 9 milliwatts, maybe you can do the design now. So let's go ahead and do the design. 9 milliwatts. So how will we do the design? We'll choose according to this expression, right? This tells you how to choose here. So we have 9 milliwatts. So 9 milliwatts means I calculate again what V0P do I require. So PL is V0P square by 2RL. So I need 1.34 volt here. I use this equation that I've derived earlier. I put 1.34 here. I'm going to give 10% harmonic distortion. So I calculate RC, comes out to be 9 ohms. Okay, so I'm sure you can smell trouble already. So, you went and told your boss that you'll give him 10 milliwatts. He asked for 9 milliwatts. Okay, he didn't ask for 10, he asked for a little less. And you calculate now, you find RC is equal to 9 ohms. All right. You want to find out now what is ICQ. So you use this equation, the saturation equation here. You put 1.34 and you calculate here. You get ICQ equal to 0.4 amperes. And so you can get 9 milliwatt, but ICQ is 0.4 amperes here. VCC is 5. And you calculate how much power will I take from the supply. VCC into ICQ 2 watts. So I'm going to give you 9 milliwatts of power, but I will take 2 watts of power from the supply. All right. So you can obviously see it's a ridiculous situation. 2 watts of power from the supply here. And all that you're delivering is 9 milliwatts. So you know now that you made a mistake by saying that I can give you 10 milliwatts. Theoretical limits are one thing. You calculated absolute value and theoretical limit of 10. But to approach the theoretical limit, there's a huge price that you have to pay. Right? And that's what you're saying. You can get 9 milliwatts, but the price that you're paying is huge here, 2 watts of power here. And obviously it's a ridiculous design. Nobody will accept it. 2 watts of power taken from the supply to deliver 9 milliwatts of power to the load here. So now, you begin to think, what can I do now? How much power then I can deliver with reasonable efficiency. There's a ridiculous efficiency here. All right. So maybe you do a design for, you're now less optimistic. You do a design for 1 milliwatt. 1 milliwatt of power. 9 milliwatt is causing so much trouble here. So you say maybe 1 milliwatt. You redo the design here. All these steps you follow. Here. You now get 14.8 milliamperes here. Now you take 74 milliwatts from the power supply. Right? 74 milliwatts from the power supply. Efficiency is 1.35% here. Okay. So now, of course, what do? This is where you are. 9 milliwatts, you've been asked to give 9 milliwatts of power to load of 100 ohms, and you find 9 milliwatts you can't deliver. Of power you can't deliver. Okay. Maybe you can deliver 1 milliwatt of power at 1.35% here. Okay. So what do? Well, you go to your boss, and obviously you're not very, you're ashamed of your design here. And so, you say, well, all that you can do is, this is what you can, 1 milliwatt of power at 1.35% efficiency. So your boss takes pity on you and says, okay, well, you can use any supply voltage. I'll relax the design for you. Okay. So fine. I still want 20 milliwatts, RL of 100 ohms. But now, let's say any supply voltage of your choice. Any transistor, any supply voltage of your choice. Okay. So which means what? Now my task even becomes harder. The more choice I have, the more trouble it is for me. I mean, I have to spend more effort on how to choose VCC. In fact, if somebody makes a choice for you, life becomes easier. When VCC was 5 volt, the design was easier. Now you have to figure out what is the optimum value of VCC. So how do we do that? So now the more freedom you have, obviously the more optimum design you can get. But the harder the design becomes. So what do you do now? Well, you set your target as 10% distortion. You go back to this equation here. VOP. Now the trouble is VCC is also unknown. RC is also unknown. VCC, RC are unknown, and RB is also unknown. Okay. and you have these two equations in front of you. So now the issue is, okay, I have all these values here. How do I choose now? If I have the freedom, how do I choose? Well, obviously I have to deliver 20 milliwatts of power to RL equal to 100 ohms. Now when I try to choose a value of VCC, I should do it with the objective of maximizing efficiency, right? I should choose a value of VCC such that while delivering this much power at this much distortion, I should maximize my efficiency. I should not draw too much power from my supply here. Okay. So what we do is we look at PL here. PL we know now is 20 milliwatts. So we calculate 2 volt here is the voltage here. And this is the efficiency here. So we'll have to do the design, meaning choosing VCC, choosing RC, and choosing RB such that the efficiency is maximized. That's your target. Okay. So what do? We have VOP by VCC here. So we take this equation and plug it here. And VOP by RL. So we can get an expression for VOP from here. Note, VOP in terms of VCC, we'll put it here. So V0P, we'll put it here. ICQ I can extract from here. ICQ is nothing but VCC minus V0P divided by RC. So I extract ICQ from here. I put it here. I extract V0P from here, put it here, and I get a nice long expression. Okay. So all that you need to do is substitute. So you get a nice long expression here, RCRL. So you must be feeling quite happy about it. You've derived a complicated expression. And now what do? We want to maximize efficiency here. Okay. So you want to maximize efficiency. So you go and look at this one, you rearrange it, and you find that my efficiency depends on, fortunately, one single parameter, which is RC by RL. All right. So you do some algebra, you rearrange it, and you find it depends on RC by RL. And you also find that RC by RL occurs in the denominator, occurs in the numerator. So, which means that there's likely to be a optimum value, which will maximize my efficiency here. So, well, you define RC by RL equal to A, let's say X, your parameter here. Let's say HD by 25, you call it A here. So you have this expression, and you take its derivative with respect to X, and you equate it to 0, and you find the optimum value of X here. So now you have found the criteria for getting the highest efficiency. How should you choose? It will tell you how to choose RC by RL. RL is fixed, so it tells you how to choose RC here. And that depends on, so you're feeling quite happy about it, you've done an optimum design. So you put in the values. So you put in the values of 10% here, harmonic distortion. So it says RC by RL should be equal to 1.18. And also tells you, if you plug in here for this value, efficiency is going to be 1.68% only. So after all this effort, you found that RC by RL value that you should have, but you also find efficiency is only 1.68% here. Anyway, so you can go forward and do the design. So how do we do the design? We know the value of RC. We know the value of RC here. We know V0P that we require 2 volts here. And so we solve this equation to get VCC here. So now you know that the optimum value of VCC is 12.9. So around 13 volt here. And once you have V0P equal to VCC minus ICQ RC, you know V0P, you know VCC, you know RC. So you get a value of ICQ. So your design is done. So you've done your design. And you've done it in an optimal manner, no guesses or anything. You've used a systematic procedure to arrive at the value of RC and the other parameters. Once you know RC, note, once you know RC and once you know ICQ, then it's trivial to determine what is RB. But then this is the best that you can do. After, even after relaxing the supply voltage requirement, all that you could do is give an efficiency of 1.7%. With 10% harmonic distortion. So now the issue is, what do you do? This is obviously not a good design. Your boss has relaxed the requirement of VCC also, right? And now is expecting a better design, and all that you can do is 1.7% efficiency. So what do you do now? Why is the efficiency low? Well, you go back and analyze why is the efficiency low, and you look at this expression here, and you find the efficiency, when I choose HD2 equal to 10%, then I get a certain efficiency here. If I take HD2 large, I'll get a better efficiency here. Okay, I'll get a better efficiency here. In fact, if you plug in a value of 25 here, say HD2 is 25%. Okay, if you plug in a value of 25%, your efficiency will not be as low as 1.7%. It will be larger. Okay, and now if you're thinking, then this is what might occur to you. Okay, that here is an amplifier, and this is its performance. So if you calculate the gain of this amplifier, how do I calculate gain? I know ICQ, so I know GM, and GM RC parallel RL is a common emitter amplifier. So you calculate the gain and you get a gain of 192, right? And now something should start working in your mind if you see this number. You know, this is an output stage, right? The specifications don't even mention gain. Nobody is interested in gain at this particular stage here. You are getting a gain of 192, and who's interested? Nobody is even asking you to give a gain of 192. All right. So now you know that you have a lot of gain, and you don't really need it. And what can you do? Sacrifice the gain and get what? If you sacrifice the gain, what do you get? You get all the benefits, and one of the benefits that you get by using negative feedback, if you sacrifice the gain, is distortion goes down, linearity increases. So all along I was telling that, you know, we were using a distortion of 10%. Why? Because I don't want my amplifier to look very bad. But suppose now I design an amplifier with a distortion of 25%. It's a pretty bad amplifier. But then what will I do? I'll put a negative feedback and I'll reduce the gain and make the amplifier linear here. So maybe then what you decide is the following: reduce distortion through negative feedback. So what you do is you go back to your original expression and you say, well, let me decide for HD2 equal to 25%. Very high distortion, 25% here. And after you do this, you find RC by RL is square root 2. And you can get efficiency as high as 8.5%. It's still low, but it's not as bad as 1%, right? So 8.5% looks better, but you're going to get high distortion. So your idea is as follows. So you redo the design, keeping in mind that it's a 25% harmonic distortion. So you have new values of RC and RB and all of that. But you know that this amplifier by itself will not work. You calculate. What you would do is you put negative feedback, you put an RE here. You put an RE here, don't bypass it, and you use it to, so you've designed it for 25%, sacrifice the gain by putting an RE here, and you will get distortion which will become less. So you use this strategy here. So you look at the gain here. So you do its analysis, ICQ is 34 milliamperes, you look at the gain is about 77, and GM is 1.3. So you want to put negative feedback. Now, negative feedback will be reducing gain. So how does the gain reduce? In this case, the gain becomes GM by 1 plus GM RE. Okay, this GM, when you put an RE here, it becomes effectively, the GM becomes GM by 1 plus GM RE. And so you want to reduce the gain, and by how much does it reduce? This factor GM RE. And remember, what happens is, the factor by which the gain reduces, the other improvements come by roughly the same factor. Roughly the same factor here. So now you have a choice. You know how much RE to put here. Let's say I take GM RE equal to roughly, let's say 9. So if I have 9 here, 9 plus 1, 10. So I'm reducing the gain by a factor of 10. So harmonic distortion should also reduce by something of the similar factor here. So you can choose a value of RE. You choose a value of RE here. So choose a value of RE of 10, right? And now, to predict distortion and all that is not so easy with the negative feedback. So you go and simulate. And you go and simulate. So you build your amplifier. Note that the amplifier was 18K here, 141, 100, 7 volt here. So you build this amplifier. You put a 10 ohm resistor here, RE. And you simulate and you find, well, when you put an RE here, there's a drop that occurs in this particular part here. Right? The current flows here, and there's a drop that occurs here. And as a result of this drop, this VCE becomes smaller. Right? Earlier, you remember all this design that you were doing it by really, saying that the transistor, you're balancing both the saturation and the harmonic distortion part. So what happens is, because of this addition, now you find you're not able to go to 2 volt when you simulate. You're not able to go to 2 volt. All that you can go is 1.5. As you try to go beyond 1.5, your transistor goes into saturation. I'm not showing you here. It starts clipping. Okay. Now with 1.5 volt, you calculate 1.5 volt, you get a power of 11 milliwatts here, V0P square by 2 RL. You look at the supply power is 233 milliwatts. You have an efficiency of 4.7%. So this is where you are. 4.7% efficiency. Distortion, you can see clearly, distortion is very small. If you look at the positive voltage here is 1.5, negative voltage is around minus 1.6, fairly low distortion. Okay, high distortion would have been a much larger discrepancy between a positive swing and a negative swing here. So this is where you are. So in fact, what had happened was one had designed this amplifier without thinking about an RE drop here, and that's why we can't reach 2 volt here. We could reach only 1.5 here. So you can go back and redesign the amplifier and redesign it not for maybe 2 volt. If you see, you designed it for 2 volt and the swing became 1.5. So maybe redo the design for maybe 2.5 volt. And after you put negative feedback and all of that RE, what may happen is it will go to 2 volt here roughly. So you redesign it for 2 volt. I'm not showing you, and then you'll get a power of around 20 milliwatts and maybe an efficiency of 5%. Okay, so that's the best that you can do now. You have a VCC now of any VCC that you could choose, right? Any RC that you could choose, any RB that you could choose. You followed a systematic procedure. You've used you've used negative feedback. You've employed all your knowledge, and this is what you end up with. So what do you do now? What is the next stage? If you want to get even higher efficiency, what do you do now? You've chosen optimum VCC, optimum RC. You put maybe optimum value of RE, and this is the best that you can do. So what's the next thing to do? Next thing to do? So the problem is not. So you will be able to get the power. The problem is efficiency is low. You want efficiency to be high, right? And why is the efficiency low? Well, power that you're taking from the supply is large. And why is the power large? Where is the power getting dissipated? It's getting dissipated in RC, and it's getting dissipated even in the transistor. So now, does it tell you where? So if this schematic can give you at the most this kind of a performance, now the only option left for you is to abandon it. You can't go forward with this common emitter schematic here. You have to leave this and go to a different circuit structure. That's the best that you could do here. Now the idea is which circuit structure? What are the options available to you? Okay, so what he's suggesting is, so this is the best that we can do. As I said, after all of this design, redesign, and all of that, we have learned how to do the best possible design for a common emitter amplifier. But we also see his efficiency is limited here. So what we need to do is look for a different circuit. One of the circuits that he's suggesting is maybe take this resistor out, RC out. Maybe too much power is getting dissipated here. You should do an analysis here at this stage that yes, for example, I'm taking 233 milliwatts of power. Only 11 milliwatts is going to the load. Where is the balance of around 220 milliwatt going? Do an analysis and see how much is dissipated here and how much is dissipated here. And if you find that a lot of it is dissipated in RC, right? A lot of it is dissipated in RC, then that may concentrate your attention on, let me substitute RC by something else. Okay. One very simple substitution that you can think of is one that we have talked about here, is that maybe you substitute it by a transistor. Will a transistor help? Well, I've done the analysis. You can check later on. Transistor may not help that much because again, you'll have a voltage drop here and you'll have a dissipation here. Earlier you were having a dissipation across RC. Now you'll have a dissipation across the transistor. things will become better, but not as much. Maybe a better solution would have been take this RC out and replace it by an element which will have no dissipation. Which an inductor. So I can take this out and put an inductor here and choose the value of inductor which is sufficiently large so that, my signal here the current here will predominantly flow through R. So inductor here will give you a large improvement in gain. I mean, in power efficiency, will give you an improvement in power efficiency. But, you don't want to use an inductor because, it's fairly large and bulky. So you don't want to do that. So then what we are at a stage where we can try this out. And as I said, if you look at the efficiency, what it's saying is this particular analysis is telling you is that, you can get an efficiency as high as, if you put HD2 equal to 25%, maybe you can get an efficiency as high as 25%, close to 25%. Okay. And, but distortion is high. So again, we'll put a resistor in the emitter to lower the distortion here. Okay. So we can use a stage like this and perhaps we can get close to 25, maybe 20% or whatever around that value. But that's all that my amplifier can do. Okay. And which means then I have to look for something else. Now, some of you may be thinking we've been talking about common collector. Maybe common collector can help. All right. So we'll see next lecture whether common collector helps. Okay. So let's stop here.